Good morning, students. Welcome to Complex Analysis live lectures. In this class, we'll discuss Taylor series and Laurent series of a complex valued function. Okay, so let's start with Taylor series because these two results involves lot of calculations. So I thought uh, we'll skip the calculation part and focus on understanding. So these results are just like problems. Okay, if we can understand the concept, then remaining is a basic routine calculation. So that is the reason I'm coming up with this PDF, which is of course prepared by myself. Okay, fine. So what is the first one is Taylor series, which says that if your f is analytic throughout the disk, mod z minus z naught is less than r naught, and then f of z has power series representation, and namely f of z is equal to, so this f of z we can write it as summation an z minus z naught whole power n. This n is from 0 to infinity, where mod z, of course this mod z minus z naught is inside this disk mod less than r naught. Okay, and what are these ans? These coefficients are given by f nth derivative, okay, evaluated at z naught upon n factorial. Okay, uh, that, and this series is called as Taylor series. Okay, fine. Now what, how will, that means what this basically says that any, if we have any analytic function throughout a disk, okay, some say mod z minus z naught is less than some r naught, then in that disk this function f of z has power series representation. F of z is equal to here. Okay. That means you can also understand that the right hand side, this series whatever we are having here, okay, this value, this converges, and that value is equal to f of z. Okay, so this above series converges to f of z, where z lies in that disk here, mod z minus z naught is less than r naught. Okay, now let's understand this picture, because I feel that most of the proof is clear once we understand this picture. How we will prove that? First, we will prove that our, by taking z naught is equal to 0. Then we can, by simply by translation, proof follows for any z naught. Okay. So if we want to understand what are all given to us, so take 0 and then just let me have some. I'll explain that picture little bit bigger so that we can understand. Okay, fine. Uh, Not even this one. We will have this. This is origin, and we will have a disk. So let me, as it is disk. So this is not okay. So this is, assume this is disk, which is distance is r naught. Okay. Then now you can take any point z in this one. Okay. So suppose we will call it. Suppose this is our a point z inside this. Okay. Now what we will do is we will consider a contour, closed contour, okay, for which this z is interior point, right? Then we can apply Cauchy integral formula. That is the idea, right? So we have taken this z. Now how we can have a closed contour? What we will do is we will take, how we do is this distance from here to here, that distance we will call it as mod z. So from this to this, okay, we will call it that as, this is mod z is equal to R. Okay, that we have taken here. Now what we do is, this is Z. Okay. Now what we'll do is, we'll consider a circle, okay, centered at 0 in such a way that that circle lies inside this given disk, and also Z is interior to that. Okay, that is this. Here what we have seen here, that we can consider now. I don't know this time that shape will come or not. Assume that this is like circle. Okay. Yeah. This is looking perfect. Like circle only. Okay, let me change that some color. Fine. Now you can see that this Z is interior to this circle. Okay. Which we can call it as this C. Right. And Z is interior to that. And we know that F is analytic. F is analytic. This radius, whichever we want to have this radius, we'll take this radius. This radius we will take it as R naught. Okay. So C naught with the positively oriented circle, and any point on this we can denote this by S. Okay. We have seen already such notation earlier. Where now what is relation? This R, we know R is less than R naught, and R naught is less than given bigger R naught. Okay. With this setup we can have now we can apply Cauchy integral formula to this contour C, because Z is interior and F is analytic inside and on C. So therefore, the value of f of Z, because Z is interior point, interior to this C, so the value of f of Z. Okay, here. Just a second. There I okay, because it is let it put in this. Yeah. Now you can see that since F is analytic inside and on C naught, and Z is interior to C, therefore by Cauchy integral formula, what we will get here is this f of Z is equal to, we can write f of Z as, so this f of Z we can write as 1 by 2 pi I integration of f of s upon s minus Z ds. Okay, over C naught, or if you call it that as C, because if you call it as C naught, it is fine. You call it this as C naught. Okay. Then the basic idea is we want to simplify this 1 by 1 minus 1 upon this 1 by s minus Z. Okay. So that you can take, so remember Z is fixed here, s is variable. Okay. So take 1 by s common, then what you will have here is 1 by 1 minus Z upon s. Then using the fact that this, if you take for example 1 by 1 minus Z, how you can write this as 1 minus Z whole in, this is 1 plus Z, okay, plus Z square plus and so on, Z power n, right? Then plus Z power n plus 1. So I'll Z power n plus 1, if we take common here, so let's explain from here, plus Z power n plus 1 plus Z power n plus 2 plus and so on. Okay, but this is same as this summation, I can write it as Z power k, okay, where k is from 0 to n or n minus 1 you take. Then from here Z power n, if I take out common, okay, what we will have here is, then again it is same as 1, then plus Z plus and so on, Z square plus and so on, but which is same as Z plus Z power n upon this 1 plus Z square is same as again 1 minus Z, right? So that means what we have written here is here. Therefore 1 by 1 minus Z is equal to summation from 0 to n minus 1 Zn plus Z power capital N by 1 minus Z. Okay. So now what we have here is Z by S. So in place of Z, you substitute Z by S and simplify. Okay. Then what we will get is this expression basically, right? Therefore, what is f of z? 1 by 2 pi integration. So whatever value we have here in this 1 by s minus z, that value we have substituted here. This is 1 by s minus z, right? And take the integration, this integration inside. Then what we have here is summation integration, summation n is equal to 0 to n minus 1 z power n by s n plus 1 f of s ds. Okay, but and this one, this whatever we are having here in this z power n will come outside. Okay, so this is z power n will come outside, f of s by s minus z s power n ds. Okay, so this you write as capital N. Okay, right? And this is, we know, because this is same as by Cauchy integral formula, fn of 0 upon n factorial. Okay, because this is z power n will come outside, f of s by s minus 0 whole power n plus 1 ds. Okay, so what we are having here is integration of f of s by s minus 0 whole power n plus 1 ds. So that is by Cauchy integral formula 2 pi I times f nth derivative evaluated at 0. Okay, that is this one upon n factorial. That is this value, and z power n is there here. Okay, that is z power n here, right? So therefore we have this one, and this entire term we are calling it as sigma n of z. Now the idea is we would like to show that this value tends to 0 as capital N tending to infinity. So our claim will be, this is our claim. Okay, this is our claim that limit this sigma n of z as n tending to infinity is 0. So that means we want to know what is this modulus of this integration. Again, by using that ML inequality, we want to know what is the maximum value it can take here. Okay, so that means we want to know what is this mod s minus z and mod f of s, right? So mod s minus z by triangle inequality is, so mod s minus z is greater than or equal to mod s minus mod z, right? And we know all what are all those values, which is nothing but mod r naught, because s is a point on the circle c naught, that means whose radius is r naught, and z is a point whose distance is r, which we have started with. Okay, but r naught is greater than r, so this is same as r naught minus, right? And take suppose m is maximum value of f of s, because it is analytic, it attains its maximum value, right? Then therefore mod sigma n of z is, so what we are getting here is mod sigma n of z is less than or equal to r power n by 2 pi m by this r naught minus r whole power into r naught power n, okay, into 2 pi r naught, because 2 pi r naught is length of the that contour, which is circle with radius r naught. Okay, now if you simplify this further, what you can do is you can simplify this into m r naught into r naught minus r, then r upon r naught whole power n. See, here r power n is there, and here r naught power n is there. So the r by r naught whole power n you will have. Now because r is, when we r is already less than, since r is strictly less than r naught, what we have here is this fraction r by r is strictly less than 1. So we know in a real sequence x power n converges to 0, okay, when n tending to infinity, provided if that value is less than 1. Okay, so therefore this limit we are getting equal to 0. That shows that limit of sigma n of z is equal to 0, right? So that proves for z naught is equal to 0. We are done. We have proved that result, that if f is analytic in that given disk, then it has a power series representation. Now we assume that suppose f of z is analytic in mod z minus z naught is less than r naught. Okay, the idea is simple. You define, take g of z as f of z plus z naught. Okay, then we can check that because our f is analytic in this one, so therefore this will be, this implies g of z is analytic. It is analytic in where mod z plus z naught minus z naught, okay, which is less than r naught. That is same as mod z is less than r naught. So g of z is analytic in the region mod z is less than r naught. So the first case what we have proved, we can apply for this g of z. So therefore this g of z has a power series representation in this mod z less than r naught. Okay. So by previous case, this g of z we can write as summation g n, that means nth degree evaluated at 0 upon n factorial into z power n, n is equal to 0 to infinity. Okay, where mod z less than r naught. Now bring back to f. Okay, how we will bring back to f? Therefore g of z is same as f of z plus z naught. Then we can observe that gn of 0 is same as fn of this z naught. Gn of 0 is same as fn of z naught. So gn of 0 is same as fn of z naught. That we can observe here by derivating n times and then substituting 0 for z. Okay, so we got this one, and then replacing z by z minus z naught, we get actually this is, okay, and that is the power series representation, and that is called Taylor series, which we have mentioned here. Okay, and as a special case, that z naught is equal to 0 is called Maclaurin series. Okay, so we have a Maclaurin series which is special case of Taylor series, and Maclaurin series is for when our z naught is the origin, z naught is equal to 0. Okay, fine. Now if f is analytic at a single point, then also it has a power series representation, because by definition of analytic, what we know, if it is analytic at a point, there exists a neighborhood where it is analytic everywhere. Okay, so take that disk, then apply the previous result, we get. Okay, so if f is analytic, at z naught, then also it has a power series representation f of z equal to whatever that one, where mod z minus z naught is less than this epsilon. Okay, for some epsilon greater than 0. Fine. Examples we'll see after proving this result, because these two are almost connected. So after finishing this, maybe in next class we'll see examples about Taylor series, Laurent series, and Maclaurin series. Okay, now this result, what we have proved is this Taylor's theorem is, if f of z is analytic, throughout a disk, what happens if f is not analytic? That means what happens if f is not analytic at a point? Then can we have some power series, some type of representation for our f of z? Okay, that is possible still, and it is due to Laurent, and we can call that series is Laurent series. What it says is that in that case, it involves f of z involves both positive and negative powers of this z or z minus z naught. Okay, so what is this theorem? Let's state the theorem, and then again we will understand through the picture. Most of the time it is about the picture, remaining all is basic calculation. Okay, so what it says is that suppose a function f is analytic throughout annular domain. Okay, so suppose we have f is analytic in the domain this mod z minus z naught is less than r1 and r2. Okay, then suppose assume that C denotes any positively oriented simple closed curve around z naught. Okay, and that lies inside that this annular domain. Okay, then at each point in that domain, in this domain, we have a representation f of z, series representation. F of z is equal to, so I can write here, f of z is equal to summation an z minus z naught whole power n, which we also seen in Taylor series. And what we have here is extra term, which is bn upon z minus z naught whole power n. N is from 1 to infinity in that annular region. Okay, and where ans are given by this integral 1 by 2 pi I f of z upon z minus z naught whole power n plus 1 dz, and bn's are nothing but f of z upon z minus z naught whole power minus n plus 1 dz. Okay, so that is the only difference, right? Now again, the proof is similar. We want to find the value of f of z, okay, in that given domain. How we'll do here is, again we prove it for when we first we will prove it for z naught is equal to 0, then we will translate. Okay, So when we want to prove it for z naught is equal to 0, let's try to understand this. What are all given to us? Then we will see what we will draw. Okay. So let me draw those shapes first. Again, if we understand this picture, then we are done. So for time being, let me drag this image. I will make it little bigger so that you can understand. Okay, then we will uh, make it smaller again. So now take this. Okay, we have here. Then we have R1, right? This annular region R1 less than R2, Z naught is 0. So let's draw that first one. Let me quickly draw a little bit. Okay. So suppose assume that this is our R naught. Okay. This is R1. We are calling it as R1 and R2. Then the bigger one. Okay. So the bigger one, let me draw a little bigger so that we can have some space. Maybe we can take even bigger. Now let me draw. We have horizon here. Okay. A smaller region which is R1, and then we will take a bigger region so that everything we can fit inside clearly. Okay. Fast. Yes. Okay. So this is our R. Okay. This is R2. Now, then what we have is that we have some C, which is a C is denotes any positively oriented simple closed contour around Z naught. That means around 0 lying in that domain. So whatever we are having C, that is here. Okay, so let me draw that with another color. So this is our C. Okay, R1, R2, C is given. Now take any Z, then what it says, if you take at any point in that domain. So suppose take this point. Let's take that point here. See, you can take that point here, here, anywhere. It may be outside C or inside C, but it should be in between R1 and R2. So as he started with this, so let's take this Z here. Okay, this is our point Z. As I said, you can take Z here also. Still you can work, right? Now what we are going to do, as I said, the Cauchy-Goursat theorem plays important role when we have this um, multiply connected domains, right? So how we do is we will form here, one is a circle, okay, in covering this one, then and another circle which is containing Z. Okay, so how we'll do here, first let's assume that this distance, whatever, like just like how we have explained, mm, this is mod Z is equal to, here mod Z is equal to R. I don't want to write there. So we'll simply put this distance is R. Okay. This distance is, now like how we did earlier, after this R we have constructed a circle containing this one, right? So that we also do same thing here. So we'll construct now two circles we'll construct. One is inside this C, okay. The other one is completely outside that C. That's all. So two circles will construct. That means that those two are our contours. Okay. So I hope I will get this time. Yeah, it is not intersecting anywhere. That is my, we can call it that as C2 according to his notation. So this is our C2, C2. Then we will have now another one which is inside to this C, okay, but in the given domain only again. That means between R1 and R2 only. Let's change this to some other color. This color. Okay. And what is this one? We will call it this as C1. This is C1. Okay. And now we can call it this distance as R1. And the another distance as R2. That means if you want this, we can call it this is my R1, and this much, which is bigger one, is our R2. That's all. Okay, this is the picture which is explained there. Now what we'll do is, somehow we want to have some smaller one, okay, which encloses this Z. Okay, so you may say, why can't we consider C2? C2 encloses Z, but it also encloses some part where F is not analytic. Okay, so for that we will construct a final one, okay, which is let's take another color, black. Okay. Yeah, this one we have taken, this is our gamma. Okay, and again it is in positive direction. Okay, so we have three, C1, C2 and gamma. Okay, now forget about this C in between, right? So what we have, if I remove this C at present, and how we will apply? Yes, so that C is removed at present to understand. Now we are going to apply Cauchy, this Cauchy-Goursat theorem for this C2, C1 and gamma. Okay, right? So therefore what we will have, because C2 is the outer contour and C1 and gamma are interior to that, so their angles, their directions should be reversed, so you will get minus minus. That's all. Okay. So what is that? If I minimize this, then by Cauchy-Goursat theorem, what we have here is integration of f of s upon s minus z ds over C2 minus, because integration of f of s upon s minus z ds over C1, because C1 should be, for according to Cauchy-Goursat theorem, C1 should be in reverse direction, but here it is in same direction. That's why we are getting minus here. That's all. Minus integration of f of s upon s minus z ds over gamma, this equal to 0 by Cauchy-Goursat theorem. Okay, where s is any point, okay, here, either here or here. Okay. Now we know that by Cauchy integral formula, this gamma, if we take, f is analytic inside and on gamma everywhere, and z is interior point. So this much we can simplify. So this we can simplify by Cauchy integral formula, which is same as 2 pi I times 2 pi I times 2 pi I times f of z. This one. Okay, so you bring it here, and then this s minus z you write as z minus s. So what you get here is f of z is equal to 1 by 2 pi I integration of f of s upon s minus z ds over C2 plus 1 by 2 pi I times integration of f of s by z minus s ds over C1. Okay, so earlier in Taylor series we have only one, here we have two. So it is just like we have to, I remember here s minus z and z minus s. Okay, that plus is here. So we have to do it two times. That's all. There is nothing different. So it calculation look bigger. Same formula you use and substitute. Okay, I'll skip those things. You can do it from here. We have explained in this. that I don't want to spend much time. That is the reason I taken PDF file. So you find out what is 1 by z minus s, okay, and 1 by s minus z, which is already calculated in earlier, okay, and then substitute those things. What we get here is this f of z is summation n is from 0 to n minus 1 a n z power n plus rho n of z plus summation bn by z power n plus sigma n of z. So we are getting two constant type, rho n of z and sigma n of z, okay, and we have two terms summations here, okay. So as n tending to infinity, we want to show that this tends to 0 as well as this tends to 0 as n tending to infinity. Then we are done. Again, how we will show this they tends to 0? We want to find the absolute value of the integral. Therefore, by using ML inequality, we want to find those values, right? So here what is a n, b n, they are all given, okay, but over c to c1, that will change to c, no problem, okay. So what is here is s minus z, z minus s. So simply find the maximum value of those values, and maximum value of f of s, you call it as again m, okay. So just like how we did in Taylor series, same way we can have it here, okay. So for rho n of z, I will write modulus of rho n of z is less than or equal to m r2 by, you forget about this constant, it is not that much. What is important is here this r upon r2, then sigma n of z is m r1 by r minus r1, r1 by r upon n. So here you have r upon r2 and r1 upon r, okay. We know that r upon r1 is less than 1. Similarly, r1 by r is also less than 1. So as n tending to infinity, these terms, right hand terms, tends to 0. So therefore, those values tends to 0. And for z naught is equal to 0, we have established, whether we have established, not yet. It is still C2 and C1 is there, but by using that deformation, we can get it, okay. You can see that as f is analytic between C2 and C and C1 and C, okay. Now that means if I go back here, okay, and if I draw my C now, okay, suppose this is my C, right? C is between, you see that f is analytic in between C2 and C. Similarly, f is analytic between C1 and C. So therefore, integration of that f over C1 is same as integration of f over C. Similarly, integration of f over C2 is same as integration of f over this C. Okay. So integration of that whatever function we have, that over C2 can be same as over C. Similarly, integration of that function over C1 is same as integration of C. Okay. That is again we are using deformation principle, right? So from that we get that here because we get that this over integration over C2 is same as integration over C, and integration over C1 is same as integration over C, right? So that proves the result for z naught is equal to 0. We are done, right? Now if z naught is any arbitrary point, then you write g of z like just like how we did in Taylor's theorem, z plus z naught. Then you find the suitable that annular region, which is R1, okay, less than mod z is less than R2, right? Then the closed contour C, which has a parameterization z is equal to z of t, okay. Now here say a is less than or equal to t is less than or equal to b, and we have here this R1 less than mod z of t minus z naught is less than R2, z minus z naught, right? So this we can change. Now we will also change the path, okay, just like how we have changed from f to g. This gamma, you take this gamma as z, which is z of t minus z naught. That means whatever we have here, this much we are selecting as new path, okay. This is just a translation by z naught, okay. Then this gamma is again simply lying in this domain that one can verify. Therefore, this g of z has Laurent representation. You write this and we substitute the values, and we will get back to the final result, which is an and bn, and Laurent series established for a function f which is analytic in the annular domain, okay. I hope only thing I skipped is this simple calculations. and that are all elementary, one can do it. Okay. uh, if you have still any doubts, you can ask me. Next class we'll discuss the examples of finding how one can find the this power series representation of given functions. Okay. If whether they are analytic, whether they are analytic in an annular domain. Okay. So we'll stop here. Please go through these two proofs and try to understand this picture. Once you understand the picture, then applying either Cauchy-Goussard theorem or Cauchy integral formula, and while simplifying, we are applying ML inequality. Okay, these three, if you apply properly, we are done. So don't just simply by heart this picture. Okay, if you see the beginning, how we started, what is given, we have written. Then what is the necessity, which curves we are considering. Okay, that is important, right? Fine. So we'll stop here and we'll see next class.